All right, to graph this function, let's go through the four major features of a graph and see what they can tell us about it. The first major feature is the x-intercepts. To find an x-intercept, you set the function equal to 0 and solve for x. Because this is a product, something times something equals 0, we can split it into two equations using the zero product property, or just common sense enough to know that if two things multiply to equal 0, that one of them must be 0. But looking at these two equations, the one on the left has no solution. That's because exponential functions can never equal 0. So that equation is meaningless, leading us to the one on the right, which can only be true, of course, if x equals 4. And that tells us that we have an x-intercept at 4, and you'll see that dot on my graph here. But knowing that we have an x-intercept at 4 isn't enough to know about the behavior near 4, so what I'm going to do is plug in a number slightly to the left of 4 and slightly to the right of 4. For example, I'll plug in 3.9 to the original function and 4.1 to the original function. The expression on the left doesn't exist, not in a real sense anyways, in a graphable sense, because the radicand is negative. You'll notice that 3.9 minus 4 is a negative number, and you can't get a real result when you square root a negative number. So nothing happens to the left of 4. So let's examine what happens to the right of 4, say at 4.1. The quantity you see in the lower right corner of your screen is a positive number. How do I know that? Well, first of all, the radical is positive. 4.1 minus 4 is a positive number, and the radical of a positive number is a positive number. But also, e to the negative 4.1 is also a positive number, because exponential functions are always positive. So since we have a positive times a positive here, I know that the y value is positive when x is 4.1. Now looking on the graph, that means that our graph will be above the x-axis, slightly to the right of 4. I've drawn it as a straight line here, but of course I'm not assuming that it's linear by any means. But I just know that the graph has to be going into the positive y value there, slightly to the right of 4. So I'll draw a straight line to indicate that. That's the first of the four major features of a graph. Let's go on to the second, which is the y-intercept. Y-intercepts are found by substituting 0 for x into the original function. But you'll notice we again get a non-real result here. Look at the radical. 0 minus 4 is a negative number. The radical of a negative number isn't real, and therefore since we don't get any real results by plugging in x equals 0, we don't actually have a y-intercept. Moving on to the third feature, the vertical asymptotes. Well, we don't have any of those in this graph. Vertical asymptotes are caused by two main algebraic characteristics of a graph. One, a logarithm, which we don't have, and second, a denominator equaling 0. Well, we don't have a denominator. So there's none of the features that create vertical asymptotes in this problem, so I don't have any. Moving on to the fourth feature is the end behavior, the direction of the graph on the far left and on the far right. To get a sense of the end behavior, I like to plug negative 1,000 and positive 1,000 into the function. First, look at the top line. When x is negative 1,000, this function doesn't exist because we have the radical of a negative, and it doesn't exist in a real sense. If you look at the top of your screen, at the original function itself, you should be pretty convinced that the only way that we're going to have a non-negative radicand is if x is 4 or higher. And so I certainly don't expect any graph to the left of 4, much less when x is negative 1,000. But now let's analyze the next equation on the bottom where x is positive 1,000. Plugging in positive 1,000 will give us a good sense of where the graph will be going on the far, far right edge of the graph. One thing worth reminding you from previous courses is what e to the negative 1,000 means. E to the negative 1,000 means the reciprocal of e to the 1,000. The reciprocal of e to the 1,000, of course, is 1 over e to the 1,000. And that being the case, I can simplify this expression so that e to the positive 1,000 is in our denominator. So here we have a fraction. We can't work it out without a calculator, but we can estimate what it might be. The numerator is the square root of 996, which is about the square root of 1,000. That's somewhere between 30 and 40. Not that you need to know that exactly, but you can imagine that the square root of 1,000 is much less than 1,000. The denominator, by contrast, e to the 1,000th power, is huge. E is such an all exponential functions are so fast growing that e to a big number is a gigantic number. E to the 1,000 is well over 1 trillion. So what is this fraction here really? It's got a numerator of about 30 or 40 and a denominator in the trillions. So what do you get when you divide, say, 40 divided by 1 trillion? Well, you get an incredibly small number, very close to 0. Now again, there's nothing special about 1,000, but plugging in a big number like this and seeing the gigantic denominator and knowing that gigantic denominators lead to incredibly small answers, we should be convinced that as x gets bigger and bigger, y is going to shrink closer and closer to 0. In math we say, as x approaches infinity, y approaches 0 for circumstances like that. Now looking at the graph, what that means is that the x-axis is going to be a horizontal asymptote of this graph, which is just a pictorial representation of the fact that we discovered by plugging in 1,000. Namely, that as x gets bigger and bigger and bigger, y gets closer and closer to 0, or becomes a very, very small number. And now that I've completed the 4 main features of the graph, the only thing left to really do is fill it in. So if you were to write this, say, on a test or a quiz, you'd be fine. And that is essentially the answer to this problem. Now remember, when we're graphing without a calculator, we're not looking for precision. So I would expect to see something that looked kind of like this on a test. But because I'm a mathematician and I do like to show students what functions actually look like, I graphed this function slightly more to scale, and I got something a little smoother than the ugly picture I just erased. But remember, when graphing without a calculator, we're not really looking for any kind of precision whatsoever, although there is now a 2-scale drawing in front of you. That completes this problem.